So we'll wrap up with a couple examples of damped motion. So just walking through this, we have A is going to be our amplitude like it was before, which is why I didn't redo it. E is a number. Remember, it's not a variable. I've got B is going to be your damping factor or the damping coefficient. T is time. That's your variable. So that's going to be what you're substituting in for. M is your mass. Omega squared is going to be used to find the period and the frequency. B is the same thing as it was over here. M is the same thing as it was over here. And T is the same thing as it was over here. So what we'll do first is we're going to write an equation when I know that the object of mass M equals 25 is attached to a cold spring with a damping factor B equals 0.5 grams per second, and it's pulled down a distance of 12 centimeters, and remember it's pulled down a distance of 12 centimeters and then released. So assume that the positive direction of the motion is up, and assume that the period of the first oscillation is 5. So T equals 5, and we are supposed to figure out what the actual equation meeting these standards is. So first of all, we do know that D of T equals A times E to the negative BT over 2M, and that's times the cosine of the square root of omega squared minus B squared over 4M squared times T. And remember that T is outside of the radical. So what do I know? I know M, so I'm going to write over here. So D of T equals A. Well, I know that A is 12, and I also know it's in a downward motion. So I've got negative 12 e to the, and now we're going to use a different color pen. Hold on, I organized. All right, we'll use red. All right, so I'm going to find out what this ratio is right here. So I've got negative B times T. So negative B is going to be negative 0.5 times T over 2 times M. So 2 times 25 is going to be 50. So this part of the equation simply becomes negative 0.5 T over 50, and that's going to be times the cosine of omega squared, and we don't know what that is yet. So just hang out for a second. Let's do a negative B squared. So I know that B squared is going to be 0.5 times 0.5. So 0.5 squared is going to be 0.25. Okay, so that's my B squared. There's your B. Square it. So I have a 0.25 over 4 times M squared. So I have over 4 times 25 squared, which is going to be over 4 times, 625. And 4 times 625, clear out of there. Stop it. 4 times 625 is 2,500. So my denominator right there is going to be a 2,500. 2,500. And we are told that T is simply going to be 5 seconds. But I need to put that in terms of omega. So we're going to use our same information that we did with just a regular harmonic motion. So what I have, using a different one, is 2 pi over omega will equal 5. Okay, so cross multiply, I get 2 pi equals omega times 5. Divide both sides by 5, but I don't want just omega, I want omega squared. So I'm going to square both sides, which is going to give me a 4 pi squared over 25. So from here, I have a 4 pi squared over 25. So this is my official equation that meets these qualifications. And so what I'm going to do at this point is I'm supposed to graph it, and then we're going to find a minimum. Okay, so I'm going to change my window so that I can see I've got a -12 up to a +12, or a -12 to a +12, and then my x's are going to be from 0 to 25 or 0 to 30. Okay, so first of all, I know it's dampening motion, so I know it's not either one of these two, because these ones don't dampen. They keep hitting that top value. They don't start tunneling out. Okay, so I know it's either A or B. So from here, I'm going to go to my y equals and clear out everything that I did before and go up here. So what I have is, based on what I just figured out, is a -12 times e to the -0.5 times x. Remember, it doesn't care if you're using x's or t's. So I've got -0.5x over 50. And then come out of there times the cosine of the square root of 4 pi squared over 25. And I'm going to go ahead and tell my calculator to put this stuff in fractions. So I've got 4 pi squared over 25 minus 0.25. Oops, sorry, hang on. So, oh my goodness. All right, hang on. I started getting ahead of myself. 4 pi squared over 25 over minus, and then I need another fraction, which is where I got ahead of myself, 0.25 over 2500, and then come out from underneath the radical and put another t or another x, or you could put it in front of the radical here. Just make sure it doesn't look like an x root. And so that's what I've got. So let's change our window. So my window, x min is going to be 0, x max is going to be 30. My scale is going to be in 5s. My y min is going to be a -12 to a +12, and my scale is 2s. So I'm going to graph that, and that's what I've got so far. And so we will notice that it is dampening as it goes, which is why we use the dampening function. Okay. And hang on, it has to think. Okay, so that's going through about 25 now. And so if that's 30, we know it's going to bottom out at 30. So I'm looking for 30, and it bottoms out at 30, whereas this one bottomed out at 25. Okay, so if I'm in increments of 5, this is 5, 10, 15, 20, 25, bottoms out there as well, but this one has more fluctuation in it. It's got 1, 2, 3, 4, 5, 6 oscillations, whereas this one only has 5. So what we're looking at then is, this is our graph, and then from here I want to find, after the first oscillation, or at the beginning of the second oscillation, what's the amplitude? So basically I want to know that value right there. And by value, I mean what's the y coordinate. So I have an option. I can either realize that this is in terms of 5. So I can substitute, in a 5 into this equation right here. So I would put a 5 here, and I'd put a 5 here, and then see what I get. Or I can use my calculator feature, and I want to calculate the minimum value because I'm bottoming out. Okay, so it's like a valley. So I'm going to hit option 3, and it's just going to randomly start floating around. I need the bottom of the second oscillation, or the start of the second oscillation. So I'm going to go a little bit to the left. It says left bound. So go a little left, then go a little bit to the right, and then it says guess, do not stop here. So get as close as you can, hit enter, let it think for a second, and it's going to tell you that you've got a minimum at -11.42. -11.42. Okay, so you know what your graph is. Now, let's talk about one more thing. If this thing keeps going on and on and on for all eternity, do you notice that it is settling in to, it's just going to end up kind of sort of petering out? And so as you get out to, if time isn't restricted, it's going to return to its rest position at 0. It's going to return to its rest position at 0. Now, when I did my simple harmonic functions, those ones oscillated back and forth like these ones, okay? So it goes up, down, up, down, up, down, up, down, up, down, and it will never, ever, ever, ever stop. So it oscillates between -12 and +12. That's not your answer. I'm just showing you an example. So that being said, now that you know how to put that in your calculator and find minimums, you can do the rest of this section. So let me know if you have questions, and you are now ready for this exam.